This is the history of E. My name is Rebecca.
I'm Ilsa.
And I'm McKenna.
All right, so almost all of the material here is directly from Eli Mayora's book, E, the Story of a Number. All right, now here we have a brief history of logs. So in the late 1550s, Copernicus's heliocentric system began to gain acceptance. Magellan circumnavigated the globe in 1521. Mercator published a world map in 1569. Galileo was laying the foundation for the science of mechanics. Kepler formulated the three laws of planetary motion, which freed astronomy from the Greek geocentric theory of the universe. And so all these developments involved large amounts of numerical data, forcing scientists to do tedious computations. So this called for an invention that would free scientists from this burden. Enter John Napier. So John Napier took up this challenge. He found that extending a geometric progression in both directions produces terms that are powers of a common ratio, such as q, and that these exponents form an arithmetic progression. For example, q to the negative 3, q to the negative 2, q to the negative 1, q to 0 equals 1, q, and so on. So in an arithmetic progression, the difference between the successive terms is constant. In this case, we have 1. This relation was the key idea behind logarithms. So he also created a table that listed the quantities for calculating subsequent powers of n, which stands for Napier logarithm, equals 10 to the 7th times 1 minus 10 to the 7th to the L power. So his main goal in this case was to reduce the enormous labor involved in trig calculations. So he followed the practice used in geometry at the time of dividing a radius of a circle into 10 million or 10 to the 7th subunits. So if we subtract from the full unit 1, 10 to the 7th part, then we get the number closest to 1 in the system, which is 0.999999, or 1 minus 10 to the 7th. So this was the common ratio, or according to Napier, the proportion that he used in constructing this table. The exponent L in this case is called the Naperian logarithm of n. So this definition, Napier's definition, differs from our modern definition, which was introduced by Euler. So Euler's definition in 1728 was that our modern definition, if n equals b to the L power, then L is a logarithm of base b of n. So in Napier's system, if L is 0, then n equals 10 to the 7th. So this means the Naperian logarithm of 10 to the 7th equals 0. Versus in our modern system, if L equals 0, then n equals 1. So like log base b of 1 equals 0. So in this case, an important difference is that because of this 1 minus 10 to the 7th, because that is less than 1, Napier's logarithms actually decrease with increasing numbers, versus our common notation, our base 10 logarithms increase. So although this is like a pretty important difference, it's actually pretty minor, and it's just based on this insistence that the unit is equal to 10 to the subunits. All right, so Napier was kind of obsessed with decimal fractions, and he just wanted to represent everything in terms of decimal fractions. And so this concern for decimal fractions kind of made a definition simpler, but it led him to come close to discovering E, actually, because he insisted on using this decimal representation. And so in 1614, he published his invention of logs in Mirifici Logarithmorum Canonis Descriptio, which is a description of the wonderful canon of logarithms. And he received actually a lot of praise for this invention, including from Kepler, who used them with great success in his elaborate calculations of the planetary orbits. Pretty cool. All right, William Oughtred. William Oughtred. So at this time, some innovators were like kind of testing the waters with mechanical devices that would perform calculations with logs because it was just so tedious. So a lot of them used a ruler on which numbers were placed so that they're in proportion to the logarithm. So for example, Edmund Gunter, he came up with a device that consisted of a single logarithmic scale along which distances could be measured and then added or subtracted with a pair of dividers. Oughtred, he came up with the idea of using two logarithmic scales that could be moved along each other. So there's two versions of this. There's the linear slide rule, which we actually learned in class, and there's the circular rule, which used two scales marked on discs that can rotate around a common point. So from 1614 to 1945, for that long, people used the slide rule, and that was actually the only way to perform exponential calculations. All right, and then William Oughtred in his Clavis Mathematicae, he introduced many mathematical symbols we use today, such as the X symbol for multiplication, the proportion symbol where you use the colons, and then he also used the tilde, which means the difference between. So in the appendix of Napier's translated Descriptio, it was actually shown, this was like the first time when E was introduced. And in this appendix, which was probably written by Oughtred, there's equivalent of a statement that log E10 equals 2.302585. Although that wasn't actually written, there was an equivalent statement. So this was the first explicit recognition of the role of number E in math. So this is just a brief note on E in the 17th century. So in the 17th century, it was marked by an enormous growth in international trade, and financial transactions of all sorts proliferated. As a result, a great deal of attention was actually paid to the law of compound interest. And it's possible that the number E received its first recognition in this context. However, we will discuss this later in the presentation when we talk about the contributions of Jacob Bernoulli. However, questions unrelated to compound interest also led to the same number at the same time in subjects such as calculus. So by the mid-1600s, the main ideas behind integral calculus were fairly well known. But what was needed was a general and systematic procedure or a set of algorithms that would allow us to solve these problems with ease and efficiency. So enter Newton and Leibniz, but we'll mostly talk about Leibniz. So this procedure was provided by Isaac Newton and Gottfried Leibniz, the inventors of calculus. So although Newton's ideas were rooted in physics, Leibniz actually shaped his ideas in a more abstract way. He thought in terms of differentials, or small increments in the values of the variables x and y, such as dx over dy or d over dy. Among others, Leibniz also discovered that the equation for the catenary, or the curve of a hanging chain, could be used as a device for calculating logarithms. And shown to the right is an actual figure of this catenary drawn by Leibniz that was shown in the book E, the Story of a Number. So the equation for this is y equals e to the ax plus e to the negative ax over 2a. And this equation was actually not given in the above form, as e at this point still didn't have a symbol, and also the exponential function was not a function in itself, but as treated as an inverse to the log function.
So moving on to Jacob Bernoulli. Jacob Bernoulli, he discovered E by studying compound interest, and compound interest is charging interest on your interest, whereas simple interest is charging interest on the base or principal amount. And the problem that Bernoulli used to discover E goes as follows. An account starts with $1 and pays 100% interest per year. If the interest is credited once at the end of the year, the value of the account at year end will be $2. What happens if the interest is computed and credited more frequently during the year? So this is what he used to discover E. And so breaking it down to what compound interest is, we'll start with the principal amount, which is the base amount. And for this example, we'll use the principal amount is $100. And the rate of interest per year is 20%. And so after the first year, we take 20% of $100, which is the principal amount, and we add it back, and we get $120 after the first year. And then for the second year, instead of adding another 20% of $100, we take 20% of $120, which is $24. And we add the 24 back to 120 so that by the end of the second year, we get $144. Then for the end of the third year, we take 20% of 144. And sorry, let me do them, get my calculator. We get 2880, and we add that back to the 144. And so by the end of the third year, you get 172.80. And then for the fourth year, you take 20% again of 172.80. And that's 34.56. And then you add that back to 172.80 to get $207.36 at the end of 4 years. And this is compound interest, whereas simple interest would be adding 20% to the $100 each year, meaning that at the end of the first year, you would have $120, then you would have 140, then 160, and then 180 by the end of the 4 years. So you can see the compound interest adds more and gives you more in the end. So if we're going to create a simple formula for creating compound interest, for the first, at the end of the first year, we would have the principal amount plus the principal amount times the rate. So we would end up with, if you simplify this equation, you would end up with P times 1 plus R. Then to create a simple formula for the end of the second year, you would simply plug in P times 1 plus R into the formula for the first. So we would have P times 1 plus R plus P times 1 plus R times R. And once simplified, you get P times 1 plus R times 1 plus R. And simplifying it again, we would have P times 1 plus R squared. And then so for the third year, again, you'd take P times 1 plus R squared, and you would plug it back in, and you would eventually get it equal to P times 1 plus R cubed. And so taking those general formulas for each year and creating a generic formula for, let's say, X amount of years, S, the total amount that you would end up with would be equal to P times 1 plus R to the X power. So taking that general formula back over here, we have for X amount of years, P times 1 plus R to the X equals S. What would happen if we wanted to compound it multiple times throughout the year and not just at the end of the year? So say we, for example, we wanted to compound it quarterly, we would have the equation of P times 1 plus R over 4 times 4 times X. We would have this multiplication of 4 right here because it is 4 times the compounding periods. And then we would have that 4 because it is 4 the amount of times that it is being broken up in a year. And so it's 4 times a year. So to create a more general equation for that, we'll use N as the amount of compounding periods. Our end equation is S equals P times 1 plus R over N times X N, with X being the number of years, N being the amount of times it's compounded yearly, R being the rate of interest, and P being the principal or like base amount. And then plugging this back into Bernoulli's equation or original problem, he had P is equal to 1, R is 100% or just 1, and then X is 1 year. So S is equal to 1 plus 1 over N to the N power. And then using this table, if you start to put in different values of N, as N approaches infinity, you notice that the equation starts to approach E. And so by the time we get to the 10 million value down here, we find that that is the value of E to the 5th digit. And so Bernoulli came up with E is equal to the limit as N approaches infinity of 1 plus 1 over N to the N power. And then moving on to Leonhard Euler from 1707 to 1783, Euler covered all realms of mathematics in his studies, including things like analysis, number theory, mechanics and hydrodynamics, topology, the theory of lunar motion, all sorts of things. And he's the reason that we use symbols such as pi and I and E and f of x. In fact, we use E because he thought that A, B, C, and D were commonly used in equations. And so he just used E because it was the next available. And he's also the most popular name in mathematics, besides possibly Newton. And he defined E as the number whose hyperbolic logarithm is equal to 1. So Euler uses his definition of the exponential function to develop it into an infinite power series. So his definition is what we saw from Bernoulli, which is e to the x equals the limit. Oh, that's weird. The limit as n approaches infinity of 1 plus, x over n. My goodness, I don't know what's going on. To the n power. And then he let x equal 1, resulting in the limit as n approaches infinity of 1 plus 1 over n to the n power equaling 1 plus 1 over 1 and so on and so forth. And then he replaced 1 over n with x over n to develop a power series of the limit as n approaches infinity of 1 plus x over n to the n power being equal to 1 plus x over n x squared, and so on and so forth. And then something else Euler proved was he also proved that every rational number can be written as a finite continued fraction, and every irrational number is an infinite continued fraction. So for example, for 13 over 8, you can break it down into 1 plus 5/8, and then you can change that into 1 plus 1. Oh my goodness. 1 over 8/5. Then 1 plus 1 over 1 plus 3/5. And so 13 over 8 is equal to 1 plus 1 over 1 plus 5. But E, however, is an infinite continued fraction, making it equal to 2 plus 1 over 1 plus 1 over 2 plus 2 over 3 plus 3 over 4 plus, and so on and so forth.
Okay, so now we are going to look at the derivative of e, or more specifically, the derivative of the function e to the power of x. And this function actually equals its own derivative, and this is just a very interesting fact because it's the only function apart from a multiplicative constant for which this is true. Here we have a brief proof of this fact, and so our goal is to find a rate of change for the function y equals b to the power of x, and then we want to show that in order for y to equal dy over dx, this b must be equal to e. So first, before we start the proof, I just want to remind everybody, it's at the top here of the definition that we just discussed, the limit definition of e, and that is the limit as n approaches infinity of 1 plus 1 over n, all to the power of n, because that is going to come up. So starting off, we have this delta x term. So when you increase x by delta x, then y is going to increase by some delta y. And in this case, that delta y is equal to b to the power of x plus delta x minus b to the power of x. But through some rules of exponentiation, we can rewrite this as b to the x quantity b to the delta x minus 1. And for simplicity, we are just going to call that delta x h. And so we obtain the required rate of change, which is this first equation that you see here, that dy over dx equals the limit as h approaches 0 of b to the x quantity b to the h minus 1 over h. So we are trying to show that that equals our original function. So since x is regarded as fixed, we can pull out this term b to the power of x to the front of the limit, yielding dy over dx equals b to the power of x, limit as h approaches 0, of quantity p to the h minus 1 over h. Now, if we denote this limit as the letter k, then we observe that if y equals b to the x, then dy over dx equals kb to the x, which then equals ky. So this means that the derivative of an exponential function is proportional to the function itself, and this term of, or the coefficient of proportionality is k, which is this limit that we've defined. So now we would like to find the particular b that allows k to equal 1, meaning that this ratio would be 1 to 1 as we want. So we can represent this as the limit as h approaches 0 of b to the power of h minus 1 over h. We set that equal to 1. And then through some algebraic manipulation, which we will omit, we can solve this equation for b. And as you can see here, we have b equals the limit as h approaches 0 of 1 plus h to the power of 1 over h. Now we just want to let m equal that 1 over h, so we can rewrite it as b equals the limit as m approaches infinity of 1 plus 1 over m raised to the power of m. And if you look back at the top, that is our definition of e, just with m's instead of n's. And so clearly we can see that this equation will only hold if b is equal to e. So thus we have proven if y equals e to the x, dy over dx also equals e to the x. And this is a fundamental result in mathematics. Going further, if we solve the differential equation dy over dx equals y, if we solve that for y, we obtain the solution y equals c e to the x, where c is an arbitrary constant. And this solution corresponds to a family of exponential curves, each corresponding to a different value of c. So that's the image here that I pulled from the Story of a Number textbook. And this just basically represents this family of exponential curves, each one corresponding to a distinct value of c. And that's just a further application of the derivative of e to the x. Okay, so any phenomenon in which the rate of change of some quantity is proportional to the quantity itself, any time that this happens, this can be governed by the differential equation dy over dx equals ay. And in this case, a determines the rate of change in each particular case. So the solution to this is y equals c e raised to ax, where the arbitrary constant c is determined by the initial condition of the system. So the value of y when x equals 0, that's what determines c. And then depending on whether a is positive or negative, this will either be exponential growth or exponential decay. Some examples of exponential growth or decay are listed below. We have the rate of decay of a radioactive substance, a hot object of temperature T0 being placed in an environment of temperature T1 and looking at the relationship of like cooling, how sound waves travel through the air, compound interest, as we looked at before, and the growth of a population. So when trying to find the inverse of the function y equals e to the x, we first start with this equation, and then we want to solve for x in terms of y, just as we've done in the past to find inverses. So we make a note that the natural log of a number y greater than 0 is the number x for which e to the x equals y. So this allows us to write x equals the natural log of y. And so then we have done what we set out to do. We wrote x in terms of y, and now we can interchange x and y. And we can see that the inverse of y equals e to the x is y equals the natural log of x. And so we have this figure also pulled from the Story of a Number textbook that just shows the top graph is y equals e to the x, the bottom is y equals the natural log of x, and they are perfectly symmetric over the line y equals x, meaning that they are in fact inverses. Okay, as McKenna discussed earlier, the power series representation of e to the x is the sum of x to the k over k factorial. It's written out there. And then just as a refresher, I put the power series representations of cosine of x and sine of x because we are going to use those in this next little proof. So here we want to prove, just find the trigonometric identities involving e that we've used in the past for so long. So we'll start above, or we'll start, and using the definition above, if you plug in ix instead of x, it yields the sum 1 plus ix plus ix squared over 2 factorial, and so on. And then from there, you can use, powers of I, and this will turn into an somewhat alternating sum, so then we can rewrite as 1 plus ix minus x squared over 2 factorial minus ix cubed over 3 factorial plus x to the 4th over 4 factorial, and this just sort of goes on. So then we can split this sum into 2 different sums, and so we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and then minus plus minus plus, so that is an alternating sum. And as you can see listed above, that is the exact definition of the power series representation of cosine of x. So we know that that first term is cosine of x. The second term, we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus plus and so on. So that is sine of x, but then we have this little coefficient of I in front of it. So this yields our first trigonometric identity, that e to the ix equals cosine x plus I sine x. And then using a very similar process, you can get the fact that e to the negative ix is equal to cosine of x minus I sine x. And then if you add the two equations, if you add e to the ix plus e to the negative ix, then you will see that cosine of x equals e to the ix plus e to the negative ix over 2. And if you subtract those equations, you'll get the sign identity that the sine of x equals e to the ix minus e to the negative ix over 2I. So yeah, that is how we can use the power series representations to find trigonometric identities that students are using every day. Okay, and now just some cool properties about E. So in 1737, Euler proved that E is irrational, meaning that it cannot be represented as a fraction. And we definitely saw that with McKenna's outline of it being a continued fraction. And then in 1873, Charles Hermite proved that E is transcendental, and this means that it cannot be the solution of a polynomial equation with integer coefficients. And then later on, in 1934, Alexander Galfond proved that e to the power of pi is also transcendental, which is just very curious. E as a concept can be represented geometrically in a lot of different ways. So the first one is, if you think about the area under the curve e to the x from negative infinity to 1, that area or that integral is equal to e. Another way of thinking about it is e is the slope of e to the x at the point x equals 1, which makes sense. And then another interpretation is the area under the hyperbola y equals 1 over x from x equals 1 to x equals e. That area is 1. So then you can use that to kind of like geometrically see what e looks like and how it behaves with the hyperbola. Then just some other cool properties. E to the power of a complex number, which is written here as x plus iy, this eventually becomes real. And this is, a more complicated process that I did not have time to show you, but it is pretty cool. This seemingly obvious thing is that e to the power of the natural log of x is equal to x for any x, and that's because those functions are inverses, as we showed. And then last but not least, e to the pi and pi to the e are actually surprisingly close in value. I have their values written down there. And it's just overall pretty interesting that the two big numbers in math, the big irrational numbers that have so much meaning and applications in math, are very, very close to each other on the number line, given how many numbers exist. So it's just kind of curious that e and pi are so close, and their relationships with each other kind of show some interesting things as well. So yeah, that is all we have to talk about E.